three-dimensional structure of molecules. And remember I said in terms of the real biggies, the pervasive concepts in organic chemistry, stereochemistry is one of the defining ones. And it's also one of the fun ones and one that really sets us apart from general chemistry in terms of how we think about molecular structure. Because stereochemistry is spatial, it's not calculational, it's looking, it's thinking, it's understanding different patterns and relationships. We'll learn a few terms along the way, like enantiomers, diastereomers, compounds. These terms themselves are not definitions, they're synopses of concepts, and it really is the concepts, not the words, that is the big part of what we're going to be learning. Let me start out by drawing two molecules, two stereoisomers, and we're going to talk about them in relationship to each other, some other structures, and then we'll move on to yet some others. So the molecules that I'm going to draw are cyclopropanes. And at two different positions, we'll call them the 1 and 2 positions on the rings, we're going to attach methyl groups. In one molecule, the methyl groups will both point up, and we'll have hydrogens pointing down. I'm trying to represent pointing up by wedges and pointing down by dashes. In the other molecule, I'll have one of them pointing up, one methyl group pointing up, and the other methyl group pointing down, putting my hydrogens. Sometimes you'll see hydrogens drawn in explicitly. Sometimes you'll not see them drawn in explicitly. Depends in part what one's trying to show. Obviously, these two molecules are different. You can see that they're different. I'm going to project out physical models. Who brought your cyclopropanes today? Who has a cyclopropane? All right, so let's stick a couple of methyl groups onto them. Let's see if I can get a video up here. Let's see, I think I've concluded that the best background for these molecules is actually my shirt, rather than trying to use the table. And so you can see our cyclopropanes, you can see the methyls are in different orientations. And you can also see this isn't just a conformational issue. When we did our gauche butane, or when we did one or the other chair cyclohexane, you could wiggle, you could flip your molecule, and it would interconvert. Those are conformers, conformational isomers. They're in general not compounds that you can isolate, separate, and put into bottles. But in this case, in the case of the cis isomer, the one I'm holding in my right hand and your left, and the trans isomer, these are two separate compounds. They're compounds that you can put into a bottle. I'll write out the names of them. We can talk about what types of stereoisomers they are. So the molecule on the left is cis 1,2-dimethyl cyclopropane. The molecule on the right is trans 1,2-dimethyl cyclopropane. So I'll write this cis for the left one and trans hyphen 1,2-dimethyl cyclopropane. You notice you're right, that dimethyl cyclopropane, all as one word. These two molecules are stereoisomers, and I'm going to spend a little time writing out definitions. As I said, the definitions really in their own don't carry much weight. It's the concepts behind them. This isn't a dictionary game. This isn't something where you just learn some words. The words are much more related to those structures and to these structures. So stereoisomers are isomers with the same connectivity, but a different arrangement of atoms in space. And by that I mean in both of the molecules you have a three-membered ring. In both of the molecules you have a methyl group on one carbon of the three-membered ring and a methyl group on the other carbon. And yet, in one case, the methyl groups both point on the same side of the ring, and in the other case, they point on opposite sides of the ring. So same connectivity, but a different 3D arrangement in space. I'm going to contrast that with the following molecules. Let's take our let's take our cis 1,2-dimethyl cyclopropane again. I'll write it without the hydrogens this time. I could also write it like this. All of these are representations of the same thing. And I'm going to contrast it with the following molecule. I'll contrast it with cyclopentane. And you notice these two molecules both have the same molecular formula. They're both C5H10. But obviously, they have a very different connectivity. We would call these two molecules, the dimethyl cyclopropane and the cyclopentane, constitutional isomers. In other words, they have the same formula. That's, of course, the definition of an isomer, equal molecule, iso equal or molecule. But they have very different connectivity. All right, what I want to do now is to classify our stereoisomers into two types, enantiomers and diastereomers, and to develop some of the concepts and some of the spatial relationships associated with these. So we're going to come back to our cyclopropanes in a minute, but let me give you enantiomers. Enantiomers are stereoisomers that are non-superimposable mirror images. Definition that I've written is really a litmus test. If you're unsure, ask yourself, are the two structures mirror images, whether two molecules are enantiomers? And can they be placed on top of each other if we rotate, manipulate, and so forth? Oftentimes in my thought processes, and yours very soon, I hope, you'll see a series of patterns and you won't even need to go through any sort of physical comparison or the mirror images. You'll say, oh yeah, he inverted this asymmetric center. Of course they're enantiomers. So I'll give you several different equivalent ways of looking at molecules. Let's start with the following. So I'm going to start with 2-butanol. You notice I'm sneaking in names as we go along. When you get to alcohols, you'll learn formally about the nomenclature. But this just means it's a butane chain with an alcohol and hydroxy group at the 2 position. And you can write the molecule like this. All I'm doing here is saying we have an OH group and an ethyl group and a methyl group and a hydrogen on this carbon. I haven't explicitly shown the 3D structure, but obviously, in making it, it's there. In other words, that representation is just showing the connectivity. I'm going to give a different representation that shows 3D structures, still the same molecule, but now I'm specifying which way the OH group and the hydrogen group are attached at this carbon. And it's the same whether I write it like this or whether I don't show the hydrogen and just leave it implied. Those are both the same. But I'm going to contrast them with the following. If I throw the OH group back behind the plane of the blackboard and have the hydrogen coming out instead of this one on your left, where I have the OH group pointing out, the hydrogen coming back. And again, I can represent them either way. So now I've explicitly shown the stereochemistry of the 2-butanol, and you can see we have 2 stereoisomers, and I'm sure by now you understand that these 2 are enantiomers. Let me show you what I mean by mirror images. What I've done with the molecules, I simply have pre-assembled the molecule on your right and the molecule on your left. And I'm going to go over to the camera now, and I'll just show you my feeble attempts to superimpose them upon each other. So let's see if I can get far enough back. Now it's a little hard to see. I'm looking at myself right now. You're looking at me too. It's a little hard. You don't get that much shading, but I think you can see the molecule on your right has the OH group coming back toward me. You can see me rotating it, the red atom. Red is oxygen. The molecule on your left has it coming out. And now I'm going to try to superimpose them, and I can get the oxygens and the hydrogens to go on top of each other, but then I have ethyl group on top of methyl group. Or I can flip it around and I can get the ethyl groups and the methyl groups on top of each other, but now in one case I have the oxygen going back and the oxygen coming forward. These 2 molecules are non-superimposable and they're mirror images of each other. What do I mean by mirror images? I mean that if I pretended I had a mirror between them, I would reflect the molecule on one side into the molecule on the other. You know how everything's backwards in a mirror? That's why it's hard for me to be up here, because I'm looking at the opposite side of the molecule, so I'm constantly having to say my right or your right when I'm talking about my left. In case you're having trouble here, I also have made it certainly easier to visualize on the screen when you have some nice computer models here. So I've made the 2 molecules as computer models. Who ended up downloading and playing with the software a little bit? Fun? Yeah, it is kind of fun. So I just made this for myself to project here, but it's sort of nice. I realize a lot of the things that I like to play around with are also fun for you. I've linked my web pages to it. So what I'm going to do is here on the molecule on the left, this is just to make it nice and pretty. I'll make it maximum quality. I'll go to show, and I'll show sticks. And then on the other one, I'm going to do the same thing. So I'll go to display. If I were doing it for myself, I wouldn't bother to go to the trouble of making it better quality, but I want it to be nice for you. All right, so here you can see that no matter how I rotate the molecules, you can see that they're mirror images of each other. And you can probably see that no matter how I rotate them, there'd be no way to put one on top of the other. All right, so I'm going to use the video here, and let's get back to some definitions. All right. The molecule 2-butanol is chiral. Whether I draw it that way, showing specifically the tetrahedral asymmetric center, or I draw it without showing it explicitly, it's still there, built into the connectivity of the molecule. That molecule is handed just like my left hand and my right hand are handed, just like my left hand and my right hand can't be superimposed on each other. They're complementary, they're mirror images. But of course, if I had two left hands, I could literally place one hand on the back of the other. Instead, I have to place them back to front. They're not the same. We say that 2-butanol is chiral. It's not superimposable on its mirror image. That's another way of saying it. And we call carbon 2, that's the carbon with the OH attached to it. It's the one that gives it 2-butanol in its name, is technically called a tetrahedral asymmetric center. One S in asymmetric, please. Often people will call it a chiral center. Not really wrong, but it technically tetrahedral asymmetric center is a little bit better. It's a tetrahedral atom with 4 different substituents. As I said, sometimes it's called a chiral center or an asymmetric center. Now, I want to contrast our 2-butanol with another molecule, another alcohol, and we'll actually go to a smaller alcohol, isopropanol or 2-propanol. And I'm just going to write it the exact same way I did on the other blackboard. I'll start out writing it, not pointing out that the carbon is tetrahedral. And then just as I on the other blackboard explicitly wrote in the OH and the hydrogen, I'll do so over here. And I'm going to write it just the way I wrote it on the left-hand side there, just the way I wrote it on the right-hand side. What can we say about these two drawings? They are indeed mirror images. but they're not enantiomers. They are they are superimposable mirror images, not non-superimposable. In other words, they are the self-same thing. They're just two different drawings of the exact same molecule. I'll just write same, not different, just to be really explicit. All right, so we would say 2-propanol is achiral. It's not chiral. If you want to be technical, you could say, because I applied the litmus test, because I checked and found it was superimposable on its mirror image, if I just took the structure on the left, won't even project it, and spun it around, I have the structure on the right. You could also look at the molecule and say, oh, of course it's achiral. It has no tetrahedral asymmetric center in it. And that's probably what I would do rather than any sort of mathematical, any sort of spatial manipulations. So let's come to a couple of definitions, and I'll write them out explicitly for you. Stuff that I've been talking about. So I'm going to give you a slight generalization here. We could say that a molecule with a tetrahedral asymmetric center is generally chiral. And the generally is largely a qualification I'm putting in for myself, because I can come up with some very, very, very specialized circumstances in which there was rapid inversion of a center. But if you want to omit that word generally, you can do so from your notes. And a molecule with a plane of symmetry is achiral. And here's our 2-propanol again. And I'll just point out the plane of symmetry is right down the center. In other words, I can reflect the right half of the molecule into the left half through my piece of paper here. There's a plane of symmetry built into that molecule. And the more you see of these examples, the easier it is to really get the hang of them. Let's try a couple of more examples. Let's try 2-butanone. Chiral or achiral? Achiral, right. Why is it achiral? Plane of symmetry. Where's the plane of symmetry? What? Well, there is. It's actually in the black form, if you think about it. So, in other words, if I reflect, there's a plane of symmetry right here. If I reflect the front of the molecule goes into the back, you could put it another way. The whole skeleton lies in a plane, and hence you have a plane of symmetry in the skeleton. The hydrogens are pointing out. Another way to look at it, equally accurate, is to say there's no tetrahedral asymmetric center. And there are only some very special cases, called Tetroisomers, where you have molecules locked through rotation into mirror images that actually can be separated. I mentioned early on when I talked about 2-butane, I said the gauche conformer and at 60 degrees is actually the mirror image of the gauche conformer at 300 degrees. Technically, those are two non-superimposable mirror images, but they interconvert millions and millions of times, billions of times per second, so no one would say you can isolate enantiomers. But there are very special molecules where they are locked into a rigidity, into a chirality without having any tetrahedral asymmetric atoms in there. All right, let's take another one. I'm not going to write it out explicitly, but let's take fluorochlorobromomethane. So I'm going to write achiral here. What about CHFCl? Carbon with a hydrogen, a chlorine, a fluorine, and a bromine attached. Chiral. Why is it chiral? Every single atom is different size, or more specifically, different. So a carbon with 4 things attached to it, 4 different things attached to it, is a tetrahedral asymmetric center. In 2-butanol, which I've now erased, on that tetrahedral asymmetric center, we had an oxygen, an OH group, we had a hydrogen, we had an ethyl group, and we had an ethyl group. In the case of bromochloromethane, we have attached to one carbon a bromine, a chlorine, a fluorine, and a hydrogen. And if you want to do the experiment, all you do is you draw the molecule. If you want to see it for yourself, you draw the molecule like so. You draw its mirror image. I'm putting a mirror plane right here. And then you check, is the molecule on the right superimposable on the molecule on the left? And you find very quickly that the answer is no. These are non-superimposable mirror images. In other words, bromochlorofluoromethane is chiral. We started by talking about stereoisomers. And we said that stereoisomers was the generic, the broad term for molecules that have the same connectivity, but a different arrangement of atoms in space. There are two main types of stereoisomers, enantiomers, and the other is diastereomers. Diastereomers are stereoisomers that are not enantiomers. the question pertains to conical Prelog notation, and it's about priorities. So we will come to how we name atoms. We assign priority to atoms. The lowest atomic number. So this is a system where we are going to very soon learn to identify our tetrahedral asymmetric centers as either being what's called R, rectus, right, or S, sinister, left. And what we're going to find is that there are some rules. It's just a formalism for saying we'll call this substituent number 1, substituent number 2, substituent 3, substituent 4. And those priorities are based first and foremost on atomic number, and then they come to substituents on the atom and so forth. It actually is a formalism. It's just a way of naming it. Just as if I decided, and everyone in the world and you decided your name was Lisa. I don't know what your name is, but if they decided it was Lisa, if you decided to, and the paperwork and driver's license, you would be Lisa. So we define right and left in this way. We'll come to that. All right, so let's look at diastereomers, and those are what we had on the blackboard when I started and introduced the concept of stereoisomers. Here is our cis and trans 1,2-dimethyl cyclopropane that I drew before. These molecules have the same connectivity. They're stereoisomers, but they're obviously they are not mirror images of each other. Hence, since they're not enantiomers, they're not non-superimposable mirror images, they are diastereomers. I'll write this explicitly. And let me contrast this, because we're doing this actually, after you've done this a while, for Buck and for Joni, this is easy, because they've seen these, they can see these structures on the blackboard, and they're literally just spinning them in their mind, doing these comparisons. But the first time you see it, it's like, oh, this is all new, this is all different, this is all kind of hard and confusing, plus we've got all these terms on top. So, okay, so let's try. Let's try this. Versus this. What's the relationship of those two structures? Somebody else. Somebody toward the back. I want to hear somebody yell out or see a hand go up. What's the relationship of the structure on the left and the structure on the right? I heard over.
Yeah, you flip it.
You flip it, exactly, beautiful. You flip it, you pick it up, you flip it over. And if you want to see it on the camera, because I know by the back row it's kind of hard to see, assuming I haven't lost my camera. Here we go. So here they are pointing up. You rotate it. Oh. There you go. Here they are pointing up. You rotate it, they're pointing down. In other words, the technical term for this is just, these are the same. Let me throw a little button here and get my camera back. All right, let's try one more. doing little bits of mental gymnastics with our molecules, and part of the reason we're doing this is just like you go to the gym to exercise your body, here you are literally exercising your mind, exercising your spatial thinking about molecules. So let's go ahead and I'm going to write this molecule, and I'm going to put the hydrogen up and the methyl down here, and then the methyl up and the hydrogen down. What about those two structures? If you have a cyclopropane, do like I'm doing right now. If you have two, all the better. Take your cyclopropane, put on your methyl groups, and actually make, best if you have two, make both of them, or with your neighbor, make one, and then your neighbor make the other. Noises that I like. I hear popping noises and ohs and ahs and revelation. That's fun. All right, so here are my molecules. And I have the molecule on, hopefully I've got it the way I've drawn it on the blackboard. I've got the cyclopropane on your left and the cyclopropane on the right. And you can see that they're mirror images. In other words, there's a mirror plane right here between them. I've reflected this into this. Put another way, I've inverted this tetrahedral asymmetric center, swapping the methyl group and the hydrogen, and I've done the same over here. And so I have my two molecules, and now we're in the same conundrum as 2-butanol. I can put the cyclopropanes on top of each other, but the methyl groups point in opposite directions. I can put the methyl groups on top of each other, but the cyclopropanes point in opposite directions. And that is the definition of enantiomers, non-superimposable mirror images. All right, this is one of the reasons why I very much like the physical models, because they really help us see these relationships. After a while, you can start to do this in your head. You can start to say, oh, I spin this structure around, and then I have the analog with the methyl pointing down and the hydrogens pointing up. You can go and say, with just paper, I spin it, but initially having a touchable, tangible molecule is very, very valuable. All right, I want to take one kind of extended example to finish things off here. And I'm going to write out stereoisomers of 2-methyl 1-cyclopentanol. All right. I'm going to make it look easy to write out well, you're going to think it's hard to write out 4 different structures. I'm going to show you what I'm doing as I'm going along. So I'm writing 4 different structures, or 4 cyclopentanols. I'm going to, on the first one, have the OH pointing out, a hydroxy group pointing out, and a methyl group pointing out, and a hydrogen going back, and a hydrogen going back. On this one, don't bother to build the molecules, just draw it along with me. And we'll call this one A, because I'm about to make some comparisons among them. And then I'll do the same thing, a cyclopentanol, but I'm going to throw the OH group pointing back and the methyl group pointing back. And I'll have our hydrogens pointing forward. And we'll call this one B. I'm permuting, by the way, in case you're wondering what I'm doing here. I'm permuting the various structural drawings. The third one, I'll leave the OH pointing back and have the methyl group now. I'll permute that to go forward and have our hydrogen coming back. And we'll call that C. And the fourth one, I'll flip things around, have our OH coming out, and our hydrogen going back on top. And then I'll have our hydrogen coming out, and our methyl group going back on the bottom. We'll call this one D. Now, obviously, A, B, C, and D are stereoisomers. They have the same connectivity. And yet, we can certainly see in some cases they're not the same. In some cases, you have the methyl groups and the methyl group and the OH on opposite sides of the ring. We call that trans stereochemistry. And in other cases, we have that on the same side of the ring. We call that cis stereochemistry. Let's take a look at A and B. I'm going to do this with models, and I made up a web page for that. I think it's an easy one to do with computer models. And so I have these molecules on my page titled Diastereomers. And I'll just make one. And I'll go click on the other. And they're in the same order as they are on the blackboard here. How are we doing on the position up here? to butanol. And there we go. Get them both up. And I'm going to go ahead and make them nice. Display quality, maximum quality, show sticks to make them nice. And I will do the same over here. Display quality, maximum quality, show sticks to make them nice. All right, so if we look at these two structures and I manipulate them, I think we can see that A and B are mirror images. They're not superimposable on each other. I've reflected through this plane here. I've got one, I've got the other. In other words, A and B are enantiomers. And now I'm going to do the same for C and D. Here's C. Here's D. Show sticks so you can see it well. Okay, same thing. I'm just going to rotate them and try to compare them. And this is the same thing you can do with plastic models as well. So what's the relationship of C and of D? Enantiomers. They're non-superimposable mirror images. Here, just for fun, I'll rock each of these structures so you can get a little bit better view of the 3D structure. So C and D are enantiomers. So we're using enantiomer in a relational term. In other words, one is the enantiomer of the other. That's a way of saying your mirror images. A is one enantiomer, B is another enantiomer. We're comparing them. Now, if we go to A and C, obviously they're not enantiomers. The methyl group and the OH are on the same side of the ring in A. They're on opposite sides of the ring in C. Stereoisomers that aren't enantiomers are diastereomers. And all of the other relationships for this set are the same. A and D are also diastereomers. A is a cis stereoisomer. D is a trans stereoisomer. Cis and trans stereoisomers are a type of diastereomer. B and C are also diastereomers, and again, B is a cis stereoisomer, C is a trans stereoisomer. They're not mirror images of each other, yet they're stereoisomers, so they're diastereomers. And finally, B and D are also diastereomers. All right, well that finishes up this discussion. If you want to play on your own and you like these exercises, go ahead and try to look at the Sudafed stereoisomers here on this page. And you can do the same thing. Even if you don't launch the software, you can open this page with the password and fill them with your molecular models. It's a great exercise.